Okay, so today we're going to be moving on to multiple linear regression. So mentioned this term before. When we say multiple as opposed to simple linear regression, we're taking the generalization where we now can have multiple explanatory variables. When we talked about simple linear regression, we had exactly one explanatory variable. Okay, so we'll call this multiple linear regression. Okay, and I can abbreviate this MLR. Okay, so we have P explanatory variables. Now, before I introduce all the notation, let me just give you a quick example. So as I've been sharing with you, Florida is known for a number of things. So we've talked about alligators, we've talked about oranges, and so one maybe what's still well known, but maybe less well known, is the fact that Florida is one of the launch sites that NASA used over the years for sending astronauts into space. And so these guys got retired a while ago. A picture here for you. So this is the NASA's space shuttle, which took its last mission in the early 2010s. So it's been a few years since these workhorses for bringing goods to the space station and taking astronauts into orbit. So this was one of the primary vehicles used by NASA for a few decades. And so tucked into Florida's coast is Cape Canaveral, which was one of the launch sites for these shuttles. And quite fittingly, that east coast of Florida is called the Space Coast for that very reason. So you can imagine as things like these complicated contraptions, like this shuttle was designed, experiments had to be done where, for example, in designing a rocket for these things, that there be multiple variables that scientists would be trying different settings of to find an optimum. And so imagine, so let's just give a very simple example based on some data I saw. So let's write down a few relevant variables. So we have let's call this the nozzle area, so in the experiment, they tried a large and a small nozzle, and then another key variable is what goes into the propellant. So engineers would tell us that the mixture in the propellant would consist of parts fuel and parts oxidizer, and so the ratio, so the variable they measured here and tried different settings of was the ratio of oxidizer to fuel. And okay, there's others, but for now let's just keep it at these two predictors and then a response. Let's call it thrust in the rocket. So so I'm just giving you a sense of this context for multiple linear regression framework. So in this case, we can suppose our response is thrust. Now, and here the reason one of the reasons I give this example is you can have categories as predictors, and we'll see in more detail later how to handle things like categorical variables. So here you see, just for simplicity, we have large and small. So we can code up an x. We can say x, and call this x1. So it can be 1 or 0. So we can just label 1 to be large, and then 0 to be small. So that's how we can code up categorical variables in regression models. And then this mixture is just number. So this fits our usual framework. Let's call this x2. It's a continuous predictor. So the idea here is that anytime you're using multiple variables, so they can be a combination of categorical ones and also continuous ones. So here's just 2 for simplicity. We are in the case where we are looking at multiple linear regression. Okay, so back to here. So the context is there's multiple explanatory variables, and we want to develop a linear relationship between y and the response y and these variables. So x1, x2. In general case, xp. So we'll call p the number of explanatory variables. Okay, so to do that, we need to generalize. So this is why we started with the simple linear regression models, and now we're going to generalize and take that framework and apply it to multiple random variables. Now, the key here to note is that because we are moving from one predictor to multiple predictors, we're going to have to do a bit of linear algebra. Okay, so I will go through that a little slower because I suppose many of us don't necessarily remember all the facts about vectors and matrices. So I will review as I go along. And at the end, I will also give you some additional references in case you're still feeling a little rusty about your linear algebra. Okay, so with that said, let's go ahead and develop this model. So our data consists of, so we'll follow the same framework. So we have n observations. Okay, so now what is so in the simple linear regression case, each observation was a pair, xi, yi. Okay, in this case, each observation now consists of both not just x and y, but you have the y and then a bunch of predictors, x's. So let's say here, so each consists of the response and the explanatory variables. Okay, so we can write this as yi. So the ith observation we can denote our recorded value as yi, and then we have a recording for each of these. So we're going to have to use double subscripts. So we'll call it xi1, xi2 up to xi p. Okay, so we use the first index to denote the number of the observation, and then the second index, 1 to p, as each predictor or explanatory variable. Okay, so this is data record. Then our natural model generalization. So then we conceptualize the model for the ith response. So then our model would state that as a random variable, yi would have the natural generalization to simple linear regression. So now the mean part is the linear combination of all of the predictors, so beta 0 intercept and then beta 1 x 1 1 x I1, and then you have this second parameter associated with x I2, and so on, x. And then xp would have parameter beta p x I p, and then finally our error term sigma squared. Okay, so that's the generalization. We have now p plus 1 parameters with the intercept beta 0, and then we have the p parameters beta 1 up to beta p associated with the p axis. Okay, and as before, we're going to assume that we have independent error terms. Okay, so this part we can call, in our usual notation, this part we can call the mean component. So this is e of yi, which we can call mu I, just for short. And so, okay, so that's the normal distribution that's assumed in multiple linear regression. And we can also, of course, or alternatively, we can write this as yi equals, so we can take this mean part, mu I, as defined here, and we can also write this in terms of the epsilons that we're familiar with. So where epsilon I is normal 0 sigma squared, and they're all independent and have the same distribution, so ID. Okay, so that's the generalization when we have p predictors. Okay, so this is writing each yi on its own. Now, to make the derivations a little more tractable, it actually helps to write this in matrix and vector form. Okay, so let's start gentle. Okay, so let's take these y's. Okay, so let's write these y's in the vector form. Okay, so it will help when we do our estimation and do our inference. Okay, so let's start like this. So we can write in vector and matrix form. Okay, so let's start here. So let's write y1, y2, up to yn. Okay, so this first step, I'm just going to stack everything together. So I'm not going to do very much. So based on this expression, so I'm going to write this as just stack everything together. So first row will be just beta 0, beta 1, x 1 1 up to beta p x 1 p. Okay, and so, okay, I'll write the next one as well. So beta 0, beta 1, x 2 1, because this is the second observation. Beta p x 2 p. Okay, and so I can do this for each of the rows. Okay, so the last one is beta 0 plus beta 1. This is nth observation, first x, up to beta p x, nth observation, and then p predictor. Okay, and then so this is the each of these is a value for this, which represents the mean of the ith observation, and then to that we add our epsilons. Okay, so we have epsilon 1, epsilon 2, epsilon n. Okay, so that's the first step to vectorizing this. So this is just vector addition. So we add. We're just talking here. We're just adding here element by element. So y1 is this mean plus this error. So next step is to actually write this part as a matrix times a vector. So let me explain how that's done. Okay, so which we can. Okay, so let me give you the final expression which we can write as okay. So notationally, when I'm talking about a vector, I'll put the arrow. So you can see visually see it's a vector. Normally, when I type it, I would boldface it, so you can see that would be another way to express it, but that might not look as clear on the whiteboard, so I'll use a vector symbol on top. Okay, and so this can be written as a matrix X times a vector of parameters beta plus the epsilon vector. Okay, now specifically what are these forms? Okay, so I'm going to write them up here. Okay, so so when I mean y vector, it's just this vector of y's. So it's a column vector y1 up to yn. Okay, so so it's also write the dimensions here. So you can follow along that indeed these multiplications work. So this is an n by 1 matrix. So we're expressing when we write the vector y, that is this column vector. Okay, so what is x? So x has this form. Okay, so the first column is just ones. Okay, so 1, 1 to 1. And then the rest of it is just these entries of the predictors. So we're gonna have x 1 1, x 1 2, up to x 1 p, and then the same thing for our second row. So the second observation, first predictor, x 2 1, x 2 2, to x 2 p. Okay, and then we fill in the rest of this matrix. So we have x n1, x n2, x and p. Okay, so this this whole thing then you see has n rows, one for each observation, and p plus 1 column. So you have one column for each x of the p explanatory variables, and then I'm going to put here a column of ones. Okay, so this is an n by p plus 1 matrix. Okay, so beta. Okay, so the next part is beta. So we have the vector of coefficients and parameters that we're going to estimate. So beta consists of this vector. Okay, so it's exactly these parameters we see here, beta 0 up to beta b. So this one is a p by 1, p plus 1 by 1 in dimensions. And then epsilon is just this part. So okay, so epsilon is the vector of errors. So this is n by 1. Okay, so written in this form then, what we're saying is that when we do the multiplication of the matrix X with the parameter vector beta, we indeed get this. So this whole thing then is simply X times beta. Okay, and so we can verify that by the rules of matrix multiplication. Okay, so let's just run through it. So to get this first entry here, we're doing taking this first row and then this column. So first, notice that the dimensions match up. So it's n by p plus 1. So you multiply that by p plus 1 by 1. You end up with an n by 1 vector. Okay, so the first entry. So you have 1 times beta 0 plus beta 1 times x11, beta 2 times x12, and so on. Okay, so we can verify that these two guys multiplied together gives us this vector with the means. Okay, so this way of expressing the multiple linear regression setup is going to be very helpful when we work with its properties. Okay, so with that in mind, so now we have the setup of y equals x beta plus epsilon. Now, before we do the estimates, it'd be helpful to review some facts about matrix and linear algebra, and also to formalize what we call a random vector. Okay, so in this case, this vector, so these random variables, y1 up to yn, so when we put together like this, we call it a random vector. It's simply a vector of random variables. Okay, and so we know some of our rules as when it comes to apply expectation and variance on random variables, and so let's generalize that to what happens when we take vectors and matrices and multiply that on random vectors. So a lot of these expressions will look somewhat familiar because they look somewhat familiar to the scalar case when we only have one random variable. But we have to remember, even though they look similar, we're doing vector and matrix multiplication, and so we have to abide by the rules of those operations. Okay, so we call. Okay, so I'm gonna write y in a row form. So I'll write y1 to yn. Okay. And so it's equivalent of put in a row form and write a transpose. Okay, so when we talk about y, I'm always referring to the column vector y1 to yn. So it can just be written a little more in this way as well, as a row with the transpose. Okay, we call that a random vector. And as I mentioned verbally, all random vector means is a vector of random variables. And so let's derive some expectation and variance properties. Okay, so analog expectation and variance properties. Okay, so so when we talk about the expectation of a random vector, okay, so use the same notation with E, but just as applied to the vector. Okay, so when we talk about the expectation of vector, random vector, we simply take the expectation of each component, so E of y1, E of y2, up to E of yn. Okay, and so this is what we call the. So when we had one random variable, we said the expectation is its mean. So in this case, it's a mean vector. So I'll call it the mean vector. And similarly, we can take the apply variance function on the random vector. Now, this case though, since we have n random variables, this guy is variable. When we use this shorthand variance of a random vector, we mean the entire matrix of variance and covariance. Okay, so specifically, okay, so when I say random vector, this is what I'm talking about. Okay, so this is going to be an n by n matrix. And the entries tell us all the pairs of covariances among the y's. Okay, so our first entry is variance y1, and strictly speaking, this can also be written as the covariance of y1 y1. Okay, but covariance of random variable with itself is simply its variance. So I'll write this as variance y1, and then the next entry would be covariance y1 y2, and then so on, and then you get to the end, the last one would be covariance y1 yn. Okay, and then we can do the same thing. Okay, let's do one more row. So the second row, so the first term would be covariance y2 with y1, and then the next one would be covariance y2 with y2. So that's just the variance of y2, and then finally covariance y2 with yn. All right, so that's what each entry of this matrix represents. Okay, so we can fill in the rest of it the same way. So the last row will be covariance yn with y1, and then covariance yn with y2, and then so on. Last one, covariance yn, so that's variance yn. Okay, so we call this the covariance matrix. Okay, because it expresses all the pairs of covariances between the n elements of the random vector y. Some people also call this the variance covariance matrix, but I think covariance matrix is clear and shorter as a term. It does. So notice that the diagonal elements of this matrix are the covariances of each random variable with itself, and so therefore the diagonal terms can all be written as simply the variances of each of the y's. Okay, so okay, what are some of its properties? Okay, so first one to note is that it is symmetric. Okay, so why is it? What do we mean by a symmetric matrix? Okay, so you have the diagonal. So what we're saying is that it is symmetric over the diagonal. So for example, covariance y1, y2 is the same value as covariance y2, y1. And we know that is to be the case because the order in which you write the random variables of which you take in the covariance doesn't matter. So we know that by definition of covariance, these two entries are the same, and similarly, by definition of covariance yn with y1 is the same as covariance y1 with yn. So we have a symmetric matrix. And the other property to note is in linear algebra terms, it is positive semi-definite. What that means is if you take this covariance matrix, so variance random vector y, then if you take a vector of constants, A, okay, so A transpose times the covariance matrix times A, this is going to be greater than or equal to 0. That's what's meant by positive semi-definite for all so this is R n. So this is n. So A is n by 1 vector. Okay, so we will see why this positive semi-definite is important. So we just write it for now here. Okay, so remember that variance can be written as an expectation. Okay, so when we're dealing with just a single random variable, we could write the variance of y as the expectation of what? Well, it would be y minus e of y, and you square all that, take the expectation. So in the random vector case, it looks similar. So let's write the corresponding expression here. So this can also be expressed as e. Okay, so what is the expectation of? Well, because we're dealing with a vector, instead of squaring, we have to multiply. We have to multiply by the transpose. Okay, so what I mean is, we can take y minus its mean vector and multiply that. So so it's going to look like the scalar case, we square, but here we need to do multiply this vector by its transpose. Okay, so y vector minus its mean transpose. So this is the corresponding vector notation for the variance. Okay, so you'll see this looks very much like the definition of variance for a random variable. Okay, so you see y minus e of y. Okay, so, except we need to do the vector y minus e of y times its transpose. Okay, so when we talk about random vector, we now understand what is this mean vector and its covariance matrix. Okay, so now let's extend some of the properties of expectation variance. So in particular, what happens when we multiply the random vector by, say, a matrix of constants or a vector of constants. Okay, so let's define those and work on examples of that. Okay, so properties. So random vector. Okay, so we're going to say let's. I'm going to use notation A, vector A, be a vector of a 1 by n. So in particular, I'm going to specifically define as a row vector. Constants. And I'm going to use capital A be an n by n matrix of constants. Okay, and we're going to look at how what happens when you take expectation variance with a random vector multiplied by these. Okay, so again, this is like the vector analog to the properties of mean and variance in the scalar case. So first, let's look at the expectation of so this row vector times y. Okay, so in the scalar case, we learned that we can pull the constant out, and that it also holds here. So we can do vector a times the mean vector of y. Okay, so the first one. Okay, notice that the way I've defined it, what is the dimension of this thing? This is a scalar. Okay, why is it scalar? Because vector a I've defined to be 1 by n, and then the mean vector y is n by 1. So this thing is just 1 by 1. Okay, so this is just a number. Okay, but in the sense that we can pull out the constant, it applies here as well. Just notice that again that this is the multiplication of two vectors. Okay, the same is true when you do the matrix multiplication. So if matrix A multiplied by the random vector, if you take the expectation, you can take the matrix A outside times the mean vector of y. Okay, so those properties of expectation hold. Okay, the constants can come outside. Albeit, again, this is a matrix times a vector, and then this is a vector times a vector. Okay, and so we have the corresponding properties for variance. So we have variance of the vector a times random vector y. Okay, so in the scalar case, remember that a would come outside, the constant would come outside, and we would square it. So again, it's going to look like that, except it's going to have the form where the variance, the covariance matrix is going to be sandwiched in the middle, and then we're going to have A and A transpose. Okay, so it'll look like this. So A covariance matrix, and then A transpose. And then we have a similar expression for the matrix times 1. A covariance matrix, A transpose. Okay, I think it'd be helpful if I actually work out the steps to show you one of these properties. So let's prove it. Okay, so let's take this last one. Okay, and then let's show how we get that result. Okay, so let's derive that last one, derivation. Okay, so we start with variance of A times Y. Okay, so according to the definition of variance, I wrote, okay, so I just erased it, but let's remember so we need to take AY, so by definition minus the expectation of AY, and multiply that with the transpose that, so AY d of AY transpose. Okay, so let's work through the steps. So let's see how we can get A times covariance matrix of Y, A transpose. Alright, so first I'm going to apply what we said here about expectation. So this this A can come outside in this expression. Okay, so let's write that AY minus A EY, AY minus A EY transpose. Okay, and so I have A here on both of these terms. So let's so we can pull out the matrix A outside here. Okay, so let's write A Y minus EY. Okay, and then I can do the same thing here. I need more brackets though, so it's just so you don't lose track of stuff here. Okay, so we'll put A Y minus EY. Alright, and all that needs to transpose. Okay, now so the reason I wrote it like this is because we have A times something and we need to take the transpose of, let's call it B, right? So you have A times B and you need to take the transpose. And so we need to remember that you take AB and you need the transpose of that, that's B transpose A transpose. Okay, so that's the fact we'll use here. Okay, so once we do that, we get E of, okay, so this part is the same, A times Y minus E of Y. And then this part becomes, okay, so we have Y minus E of Y transpose, and then A transpose, okay, after applying this property of transpose. Okay, and so we're almost there, because now we recognize that this part, if you take the expectation of that, is by definition the variance of the random vector y. Okay, so how do we get there? Well, we just remember that A is a matrix of constant, and so is A transpose, so those can come outside the E. So we have A times expectation of the random part in this expression. Okay, so the constant has come outside, and so this is indeed, by definition, A times the covariance matrix of Y, and then A transpose. Okay, so we have shown this last property. Okay, so before we move on, I think just to help review working with matrices, let's make up a numerical example and then do some concrete calculations. Okay, so let's call this a numerical example. Okay, so let's just make some numbers up. So let's say y is a random vector, say with 3 components, y1, y2, y3, and as usual, we define it as a column vector, so put the transpose here because it's written in row form. Okay, so let's make up so suppose E of y. Okay, so let's make up a mean vector. Let's say let's say the expectation of y1 is 3, expectation of y2 is say 1, and expectation of y3 is say this is the mean vector, and let's make up a covariance matrix as well. Okay, so I'm just going to fill in some numbers. So again, remember that, okay, let's fill in the diagonal first. So suppose the variance of y1, so the first element, let's say the variance is say 4, and the variance of y2 is, let's say, 1, and is say 3. Okay, so remember the diagonal represents the variance of each individual component of this vector. Okay, and then the off-diagonal terms represent the covariances. So this entry is the covariant between, for example, y1 and y2. Now, so let's make some. Let's put some entries in here. Let's say this is, let's say a half. Let's say half. Because of symmetry. Okay, so likewise this. This top term and and this on the lower right are going to be symmetric. Okay, so and remember these are covariances, so they can be negative as well. So let's make up some number here, -2, and they can also be 0. Okay, so covariance 0 means those two components of that vector are uncorrelated. Okay, so we can put 0. So in this case, y2 and y3 have correlation 0. Okay, so let's work out an example. So I'm going to give you a vector, and let's make up a vector for A. So the way I define it, I'm going to write it as a row vector. So let's just say it's like 1, -1, 2. Okay, so this exercise here is pretty straightforward. We're just going to start by computing the mean vector and covariance matrix when we apply vector, and then we also apply a matrix. So I'm going to let's define one other. And also give you a matrix A as well. Okay, so not going to be very creative. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so based on the facts we described, we can calculate the mean and variance of these, so exercise. Okay, so we compute expectation of vector A times y, variance, and then the same with the matrix. Okay, so that'll be an exercise. Okay, so let's do a couple of these. Okay, so remember that. Okay, so in this case, y has 3 dimensions. Okay, so this one is a 1 by 3 times a 3 by 1. So this is just a scalar, and this is just a scalar. Okay, and then what about here? So this is this is the matrix. Okay, so this will be 3 by 1 mean vector, and then variance. So A times y is the covariance matrix. So this will end up being 3 by 3. Okay, so let's just do a couple of these for practice, and you can do the rest yourself to make sure you remember how to work with vectors and matrices. Okay, so let's start with the first one here. Okay, so for example, expectation of a times y, as we learned, is we can pull out the a, so we have a times the mean vector of y. Okay, and so what is a? It's this vector 1, minus 1, and 2. And then I'm multiplying by the mean vector of y, so this is 3, 1, and 2. Okay, and so we do multiplication, so 1 times 3, minus 1 times 1, and then plus 2 times 2. So in other words, the mean of vector A times random vector y, so if I can count 2 plus 4, so this is 6. Okay, and so similarly, let's do the variance as well. A, y. Okay, so in our fact, we saw that we get this as A times the covariance matrix of y times A transpose. Okay, so let's write out the vector A, so 1, minus 1, and 2. So that needs to be multiplied by this covariance matrix. So let's copy it down. 4, half, minus 2, half, 1, 0, minus 2, 0, 3. And then I need to multiply A transpose. So A transpose transposes the row vector into column form. So we'll write this as 1, minus 1, 2. Okay, so let's finish this calculation as a way of reviewing multiplication. So this is 3 by 3 times 3 by 1, so we'll end up with 3 by 1. Okay, so let's multiply through. So 4 times 1 plus a half times minus 1, and then minus 2 times 2. So that'll give me the first entry. And then similarly for the others, so a half times 1 plus 1 times minus 1, and then 0 times 2. And the third entry, minus 2 times 1 plus 0 minus 1, and 3 times 2. Okay, so we have, after simplifying, what is this? This is minus a half. This one is minus a half. And then the last one is minus 2 plus 6, so it's 4. Okay, so now we're back down to vector with vector, so this becomes, that's why we get the scalar. 1 times half minus 1 times minus half, and then plus 2 times 4. Okay, so that cancels, and so we just end up with 8. Okay, so this is the kind of calculation that just to illustrate and helps us review how to do these sorts of operations on vectors and matrices. And so make sure you know how to do all of these. Okay, so I'll leave these two. So you can do it on the matrix A times random vector y. Okay, so leave that to you as an exercise. Okay, now we talked about random vectors in general, giving you an introduction to that. Now specifically, what kind of random vectors and what distributions of random vectors are most important in this class? Well, not surprisingly, they are normally distributed random vectors, and specifically, we need to take the normal distribution and extend it to a normal distribution in multiple dimensions. Okay, and so that's known as the multivariate normal distribution. So I'm going to write down the density function first, and then talk about some of its properties. Okay, so you can think, well, where is the multivariate normal going to come from? Okay, so let's keep that in mind as we're talking about this. So remember, we're modeling y as matrix x times the vector parameters beta and then plus epsilon. Okay, so ultimately, after we derive and look at these properties, we're going to come back to multiple linear regression, where indeed the random vector y is going to have a multivariate normal distribution because we're assuming all of the epsilons are normally distributed, and so therefore the entire vector of response variable observations y can be written as a multivariate normal distribution. Okay, but first let's define it. Okay, so the multivariate normal distribution. Okay, I'm going to abbreviate this as MV multivariate normal. Okay, so we say that a random vector y follows a multivariate normal distribution with parameters mu and sigma. Okay, so notice that this is capital sigma. So when we used the normal distribution, we would write sigma squared here. So this is in the Greek alphabet. This is the capital of that. So we'll use capital sigma to refer to the covariance matrix. Okay, so in fact, it's parameterized this way, and given these, given this notation mu and sigma, because these are in fact the mean vector. So mu is the mean vector, and this is the covariance matrix. Okay, so in fact, in multivariate normal, we're saying E of y is mu, and the variance is the covariance, this covariance matrix. Okay, so density function. So whenever we write to specify, so we don't always write down. So when we did the T distribution, we didn't write down the density, but here I think it's helpful because you can see the connection to the normal distribution, which when we have one random variable, which should look familiar. So I'm going to write this part down. So okay, so it has a density function as follows. So it's denoted F. Okay, so it's density corresponding to this distribution. So its density is conditional on these parameters mu and sigma. Okay, so it has this form. So we have 1 over, we have 2 pi. Okay, I should be specific here and say that I'm supposing we're talking about n dimensions. Okay, so let's say, so suppose y is y1, y2 to yn. Okay, transpose. Okay, so specifically I'm talking about an n-dimensional multivariate normal. Then this 2 pi on the bottom is going to have power n over 2. And I'm going to have the determinant. Okay, so these 2 bars denote the determinant to half, and then the exponential term. So this just means e to everything in here. But since it's a bit large, so I'm going to write it as exp outside. So we have in here minus a half y minus mu as a vector, and in here we need the inverse of the covariance matrix, and then y minus mu transpose. Okay, so you don't miss it, let me just reiterate this thing is talking about the determinant. And then here, this guy is the inverse of the covariance matrix. Okay, and so the reason I write it this in this way, you can see this is entirely analogous to the form of the density function of a normal random variable. Okay, so I'll write here compare. Okay, so compare to the 1D case. Okay, I'll just write it so you see the connection. So if y is a normal distribution, remember it looks like this: 1 over root 2 pi sigma, and e to the minus y minus mu squared over 2 sigma squared. Okay, so you can see this is the multivariate analog to this density function. Okay, so instead of 2 pi to the half, we now have 2 pi to the dimension n over 2, and then sigma now is down here is the determinant, and so instead of y minus mu squared, again we have this y minus mu with the matrix multiplications with y minus mu vector with the inverse. So this inverse is analogous to sigma squared on the bottom in the 1D case. Okay, so in fact, a lot of the properties that we would expect a normal distribution to have also apply to the multivariate normal. So I'm going to end today by running through those properties, and then we're going to pick up on estimation next time. Okay, so properties. Okay, so again, let's define some constants, and then we're going to apply the facts we learned about constants multiplying on random vectors, specifically in the context of the multivariate normal. Okay, so let's set it up as follows. So suppose y, okay, so this is y1 up to yn transpose has a multivariate normal, mean vector, and covariance matrix. And I'm going to define some constants in the same way. So it's oops, my bad. One by and row vector constants, and then A is our n by n matrix of constants. Okay, so first one is that remember when we looked at normal distributions, we looked at linear combinations of normals, and they were still normally distributed. Okay, so let's look at the analog here. So when we said linear combinations, they're really just a special case of linear transformations in general. So number one is that linear transformations of a multivariate normal is multivariate normal. Okay, so again, I defined these constants here. Okay, so what is the distribution of A times Y? Let's start with the vector first. Okay, so this is multivariate normal. And, well, what does this mean in variance? Well, all we have to do now is apply what we learned earlier today about what happens to the mean and variance when you multiply this vector. Okay, so this mean is simply A times the mean vector of Y. And then for the variance part, we have A times the covariance matrix Y, so it's sigma and A transpose. Okay, so we already know that it has this mean and variance. So this property just tells us it is normal with that mean and variance. Okay, and then likewise, we can do the same for matrix A times Y. So this is multivariate normal with the mean A times mu, and then A sigma A transpose. Okay, so that's first property. Second property is that the marginal distribution of any individual random variable within the vector is normal. So when you integrate out the other y's from the joint distribution, the multivariate normal can reduce to a one-dimensional normal random variable. So specifically, we can say the marginal distribution of yi is normal. Okay, and specifically, yi is normally distributed. What's the mean and variance? Well, it's simply the ith element of the mean vector, and then the variance is the ith entry of the covariance matrix. So this is ith element of mean vector, and this is the ith element of the covariance matrix, or in other words, the ith entry of the diagonal of sigma. Okay, so this is indeed a generalization normal, because you can always go back, take a marginal, and it is our usual normal distribution. Okay, so in fact, it's more general than that. So in fact, any subset of the y's, of the yi's, is a multivariate normal. So for example, if you're primarily interested in, let's say, y1 and y2, out of the n y's we have, then y1 and y2 also have a joint multivariate normal distribution. Okay, so this connects the multivariate normal with what we know about normal distribution. Okay, thirdly, conditionals are also multivariate normal, and they have a particular form. We won't derive that today, but I'll just mention this as a fact. So conditional are also multivariate normal. So specifically, let's give an example. So what I mean by conditional is I say, okay, what's the distribution of y1 given, let's say y2 up to yn? Well, this is going to be normally distributed. So if I split up the vector and condition one part of the y vector on the other, that's going to be multivariate normal. And finally, and this one is a very special property of multivariate normal distribution, is that uncorrelatedness implies independence. So that's in general that's not true, but for multivariate normal it is true. Okay, so what I mean here is if the covariance of yi and yj in our random vector is 0. So in other words, yi and yj uncorrelated. Okay, so this is in the multivariate normal case. This is equivalent to that yi and yj are independent. Okay, so y uncorrelated. So in other words, if you're looking in the covariance matrix, so how do you know is if you look at covariance matrix sigma and you look at the ijth entry. Okay, so that is 0, then we know that those two y's, those corresponding to that entry, are actually independent. Okay, so in general this is not true. We can have uncorrelated random variables that are not independent in general, but in the special case of the multivariate normal, they are. So this is quite a useful property. Okay, I think this is a good place to stop, so I will pause for a few seconds and see if there are any questions in chat. Okay, so why does covariance 0 imply independence in the special case of a normal? Well, we can show the proof for that, and I can point you to a reference that will show this fact and why it is true. Property 3. So conditionals are also multivariate normal. So if I take let's say y has 10. Let's say there's 10 random variables in the vector y, and we know the entire random vector y is multivariate normal. So if I say if I want the distribution of, let's say, the first 4, so y1, y2, y3, and y4, given y5 up to y10, okay, so y1 to y4 conditional on y5 to y10 would be a 4-dimensional multivariate normal. And there are expressions we can derive for the particular mean and covariance matrix, mean vector and covariance matrix for that case. So this is what we mean by conditionals. So you take part of the random vector and condition on another part of the random vector. Yeah, and that reminds me. The other thing I'll mention is that. I will add a few supplementary references of materials that you can look at on the web. If you feel you're a little bit rusty with linear algebra and or want to look at some of these facts about the multivariate normal in a little more detail, I will point you to some supplementary references. And when we come back on Wednesday then, we're going to go back to our main topic, which is to use some of these facts we looked at today and do estimation. So we're going to estimate the parameters, the vector of parameters beta in the multiple linear regression model.